Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, very happy that Lionel is about to tell us about logarithmic fluctuations from circularity. Please.
Okay, thanks, Yuval. So I gave Yuval several options for what I could talk about, and this was his choice, and he insisted I don't combine it with any other topic because he wants to see the full proof. So, well, we'll see how it goes. Okay, so the title of my talk is Logarithmic Fluctuations from Circularity, and that refers to a growth model called internal DLA. I'll move this hand out to the corner so Russ doesn't get too annoyed. I hope it doesn't bother him too much hanging out up there. What is internal DLA? Many of you know. It's a very simple model. I start with n particles at the origin in Z2, and one at a time, each of them is going to perform a simple random walk until it finds an unoccupied site. In other words, a site where there are no other particles. And once it finds such a site, it stays there forever. So you run n such walks in succession, and that gives you a random set of n occupied sites in Z2. And we want to understand the shape of this random set. So here on the bottom of the slide, I'm writing out in symbols what I've written in words on the top. So I define this random set inductively. Once I have an, I define an plus 1 as the union of an with a single additional point, xn of tau n, where these x's are independent simple random walks in Z2. And tau n is the stopping time. It's the first time that this nth walk reaches a site that's not in the set an. So let me show you a simulation of what this does. So particles are starting here at the origin. There's a question, why do we have two colors? And I'll explain what the colors mean in a minute. Essentially, the red points are the ones that join the cluster earlier than expected, and the blue points join later than expected. So the set an is the union of all the red and blue squares in this picture. And you're not seeing the individual random walk steps, but you're seeing the results when they reach an unoccupied site.
Sorry, I couldn't follow the notation. Can you come back to the first?
Yeah. So, okay, you start with set A1 that's deterministic. It just consists of the origin. Then inductively you define an plus 1 is the union of an with one more point. And to find that point, what you do is you run a simple random walk, which I'll call xn, because it's supposed to be independent of all the previous walks. And I stop that walk at the time tau n when it first exits the set an. Okay. So that's the unoccupied site. And I just adjoin that point to the cluster. Now I have an plus 1. Okay, so if you run that simulation for longer, this is what you get. And you can see it's kind of strikingly circular. So what this talk is about is measuring exactly how close this set is to circular. And if you zoom in on the boundary, this is what it looks like. And well, you can really see, of course it's a random set, so you'll have some fluctuations on the boundary, but they seem to be quite small. So you have to look pretty hard even to find a single site like this, for example, which is unoccupied, but all 4 of its neighbors are occupied. Okay, so the questions, why is the limiting shape a disk, and what's the scale of the fluctuations? Let me tell you a little bit about the history of this problem. It goes back to chemists Meakin and Deutch in the 1980s, and they imagined internal DLA as a process where you have some corrosive particles, those are your random walkers, and they're diffusing in some medium, and when they reach the boundary of this medium, there's some surface, and they're corrosive, so they etch away a little bit of the surface. And the question they were interested in answering is, can you use a diffusion-limited process like internal DLA in order to etch a certain pattern or a certain design on your surface? And they concluded the answer was no, you can't make any sharply defined pattern using a diffusion-limited process because the surfaces you get are just too smooth. So in our model, that's reflected by the fact that these fluctuations from circularity are very small. And they were a little bit surprised by this finding, so they wrote, it is of some fundamental significance to know just how smooth a surface formed by diffusion-limited processes may be. And they have this quote that really made me smile when I read it, which shows that they expected, like most of us, that when you ask for fluctuations of a process that's derived from random walk, you expect some kind of square root fluctuations, or at least some kind of power law. And it's pretty clear from this quote at the bottom that that's what they expected. So they said, for them, xi is the scale of the fluctuation, and L is the size of the system. So they said initially we plotted log xi against log L, but the resulting plots were quite noticeably curved. Figure 2 shows the dependence of log xi on log L. Okay. And then they found a straight line. And so what that straight line is indicating is actually the scale of these fluctuations are only logarithmic in the system size. So parallel.
That was a physical experiment?
Yes. So I should say, so another impressive thing about this paper, I mean, it's in Journal of Chemical Physics. It doesn't prove any theorems. It was all done with computer simulations, which I think in 1986 is very impressive to find this kind of logarithmic dependence, because computer simulations back in those days couldn't get to very large scales. So. Okay, so parallel to this more applied literature, there's an independent history in the math literature.
Is not that long ago. So,
it's not that long, but with Moore's law, a few orders of magnitude long.
There was a video game where you could throw bananas at gorillas, come across like cityscapes. It was also, presumably you could simulate such a process without.
Well, it's a question of how far. Yeah.
But
I finished my
you could
undergrad.
count to 10 million or something.
Well, there's a good joke here about gorillas, bananas, and IDLA, but I'm not finding it. So. Moving on. So in math, mathematicians studied this process sort of for its own sake, unaware, I think, for a while of this literature in chemistry, starting with Diaconis and Fulton, who realized this process as a special case of an addition law of sets in ZD. So what they defined was a way to take two finite subsets of ZD and add them, and the sum is a random set whose cardinality is the sum of the cardinalities of A and B. And internal DLA is the special case of this operation when you take the singleton set consisting of just the origin and keep adding it to itself. And so motivated by this idea of Diaconis and Fulton, Lawler, Bramson, and Griffeath the next year proved this limiting shape, that in fact it is a disk in Z2 and a ball in higher dimensions. So, right, so this is saying if the number of particles I start with is, say, the closest integer to pi r squared, so I would expect it to fill up a disk of radius r, then with probability 1 for all sufficiently large r, we have that this random set contains a disk of radius 1 minus epsilon times r and is contained in a disk of radius 1 plus epsilon times r. And Lawler improved these bounds a few years later to show the fluctuations are at most order r to the 1/3 up to log factors, and said a more interesting question is whether the errors are O of r to the alpha for some alpha less than 1/3. So that's the question we're going to answer today. Okay, so the theorem which my co-authors and I proved independently and almost at the same time as two French mathematicians, Asselas and Gaudier, is that in fact you can get these fluctuations all the way down to constant times log r. And I write log squared here, but I should really update this slide. So their first paper had log squared, but then in a subsequent paper they improved it to log. So these are really two independent proofs of the same theorem. This is in 2 dimensions, and you can ask what happens in higher dimensions. It turns out there the surface is even smoother. So there that you can get down to square root of log fluctuations.
Well, these are just upper bounds, so it's not clear that it's smoother.
That's right. So, okay. So there's a question of how, are there really fluctuations that are this large? And actually, in higher dimensions, we now know the answer is yes. So square root of log r is the right answer. So that's a recent posting on the archive of Asselas and Gaudier. And in 2 dimensions, it's still open. It's at least root log r, but we think it's log r. OK, so I'm going to try to give you a picture of the proof. So what goes into the proof? Well, there's an initial ingredient which doesn't take into account the overall circular shape, and it's just kind of a local lemma about what happens if you zoom in at a point on the boundary, which says that certain formations, which we call thin tentacles, are unlikely to occur. Then so a thin tentacle, I think I have a picture on the next slide, but it's something that looks like this, where you have a point that belongs to the cluster AN. Can everyone see this? But not too many nearby points belong to it. So once we've ruled those out as unlikely, then we're going to, for each direction, so for each direction, we'll define a martingale which will detect fluctuations from circularity in that direction. And the fact that you can't have thin tentacles means, well, it strengthens these martingales. It says that, so basically the martingale is going to be defined by summing a discrete harmonic function over the cluster. And we're going to choose a function that blows up at zeta. So the fact that if zeta is in the cluster, that a lot of nearby points also have to be in the cluster really means that when you sum your discrete harmonic function that blows up there, it really is getting a large contribution from all these points near zeta. And OK, I'll say more about that. And then lastly, there's a kind of self-improvement character to the argument, or maybe bootstrapping is another way to put it. So starting from the fact that your cluster is roughly circular, you can deduce that with high probability it has to be even more circular. And you could keep going in that way all the way until the log scale. And that's when this bootstrapping breaks down. OK, yeah, so here's the picture of the thin tentacle. So OK, so precisely what is a thin tentacle? so it's a point z which belongs to the cluster AN, but the number of points in a ball of radius, some radius m around z that also belong to the cluster is small. So it's less than a small constant b times the volume of the ball. And so we show these are exponentially unlikely in m squared in higher dimensions and m squared over log m in 2 dimensions.
So z here is fixed, or there exists a z? You want to say the probability exists a z, or z is fixed?
Well, either one. I mean, you can just union bound it. I mean, these are tiny probabilities. But imagine it's fixed. It will be fixed in the proofs.
So the m and n are related how?
The only requirement is that this ball doesn't contain the origin. So,
That's it.
yeah. So let me maybe comment on why you get this m squared in the exponent here. So if you think about, what's the most naive way to form a thin tentacle? Well, here's your point z, which you want to belong to the cluster. Here's the origin, and your cluster looks something like this, but you have to get all the way out to z. Well, naively, you could just form a path directly to z, and in order for z to belong to the cluster, you have to fill in all these points of this path. So imagine that you have random walks that just, the first one visits this beginning of the path and fills it in, and then the next one walks straight up the path and fills in the next one. So your random walks just walk straight up and fill in these points. And it's going to take, so if this tentacle has length m, that's going to take, order m squared random walk steps. To get m particles to fill up this path in succession. So just this most naive way of building a tentacle already, it has this probability. So you're certainly not going to improve on this m squared. Okay, so now I'll explain what the colors meant in my simulation. So those encoded early and late points in the cluster. So we're going to measure earliness and lateness in units of the radius of the cluster. So we'll say that a point is m early, like this point here, if at the time n equals closest integer to pi r squared, it's already occupied, even though this point is outside the ball of radius r plus m. And likewise, this point here is L late because it's still not occupied, even though it's inside the ball of radius r minus L. Okay, so these are the same definitions in symbols that the picture showed. Okay, and here are the events that we want to show are unlikely. So we want to show if m and L are bigger than a constant log n, that it's unlikely that any point in an is m early, and it's unlikely that any point in this ball is L late. Okay, so here's the overall structure of the argument with this bootstrapping self-improvement step. So there are two lemmas, and they're almost symmetric. So one is that if there are no L late points, and m is bigger than a large constant times L, then with high probability there are no m early points. The other one is the other way around. So if there are no m early points, then with high probability there are no L late points. But now the arithmetic is different. So you get some savings here. You only need L to be at least the geometric mean of m and log n. So if you imagine applying these two lemmas in succession and iterating, well, if you start with there being no L late points, and you apply both lemmas, then you'll get that with high probability there's no c squared log n L, square root of c squared log n L late points. So, and this is decreasing until you get down to the scale where L is constant log n. So another way to say this, sometimes iterating makes you suspicious because you think secretly there's some constant blowing up. Another way to say the same thing is, suppose L and M are the maximal lateness and earliness occurring in any cluster A1 up through AN. So these are lowercase, but they are random variables. So you have this random point L comma M, and we want to show that it lives close to the origin, so there are no late and early points. So what we can do is say, well, as a first step, the cluster has to be path connected, so there can't be any extremely early points. Okay? So this rectangle in green up here has probability 0. You just can't have an n early point in the cluster AN. Okay, and then the two lemmas say that, well, one lemma says that this kind of half-infinite rectangle is unlikely, and the other one says that this kind of half-infinite rectangle is unlikely. So you can write down a logarithmic number of rectangles here that are all very unlikely, and then you get to this white region where the maximal earliness and lateness that occurred by time n is at most constant log n. Okay, so what goes into the proofs of these lemmas? So the basic ingredient is a martingale which detects earliness and lateness near a particular, or in a particular direction. Okay? So fix a point in Z2, zeta, and then we're going to take a discrete harmonic function, which I'll define precisely on the next slide, but it approximates this continuous harmonic function, which is essentially just a real part of 1 over zeta minus z. So this is a picture. It has a pole at zeta, and its level lines are circles. Now, the pole at z, the pole at zeta is really important here, because if we take this harmonic function and sum it over the cluster, well, we want it to detect whether there are points occupied near zeta. So, I mean, that's the reason we take it to have a pole at zeta. Of course, that also causes problems. So when you try to make a discrete harmonic function out of this thing, you find that you can't make it discrete harmonic everywhere in the whole Z2. So discrete harmonicity will fail at a few points near zeta, which means that if you want this process to be a martingale, then you need to stop your particles from reaching these bad points. So we're going to define a certain set, omega zeta, where our particles are going to stop. Okay, so this gets slightly technical, but it's sort of, the details are really important, so I decided to put them in. So the simplest case is when zeta is, say, positive real. So then we define h zeta as just a difference of two adjacent values of the potential kernel. So the potential kernel is this thing that acts like the green function for simple random walk, but because simple random walk is recurrent, you need to take a difference here. So in 3 and higher dimensions, this would be simpler. You could just delete this first term and take, so here xn is a simple random walk. So you're just counting the total expected number of visits to the site z. Okay, but that's infinite in 2 dimensions. So to kind of normalize it and keep it finite, you subtract the expected number of visits to 0 up till time n minus the expected number of visits to z. So okay, so what are the relevant properties of this AZ? It's discrete harmonic except at the origin, and its asymptotics are really well known. So it behaves like constant times log absolute value of z plus a constant plus a very small error term. And I mean, this is kind of what all these circularity arguments have in common, is that somewhere buried in the argument, you're going to use this kind of asymptotics for the potential kernel. So in our case, this h zeta we defined as a gradient, a difference of two consecutive values of this shifted potential kernel, which means, so log absolute value z, that's real part of the log of z. So this h zeta is like real part of 1 over z minus zeta plus a small error.
You don't get an even better error.
Actually, you do get an even better error, but we don't need it. So that was the case that zeta is positive real. And in general, you can do something similar where you take a linear combination of 3 different values of potential kernel. It's exactly the same, just messier. Okay. So I defined the harmonic function that we're going to use. Now I have to define the set where we're going to stop. And the set where we're going to stop is essentially a ball, but there are lots of things that are very close to a ball, and it's important to take exactly the right one. So the one we're going to take is essentially a level set of the harmonic function. So what we do is take this function, which is defined on lattice points, and extend it linearly along edges of the square grid. So now we're working with this one-dimensional grid instead of this set of discrete points. And okay. And now, so take the connected component of the origin in the set, which is this grid minus the point zeta, all the points where h zeta is at least 1 over 2 norm of zeta. So what does this look like? So here's the particular example, zeta is 6 plus 4i. Okay? So the boundary of this omega zeta consists of a whole bunch of points, typically on the middle of these grid segments, where this function h zeta is exactly equal to 1 over 2 norm of zeta. And then it also has zeta itself as a boundary point. So the important arithmetic here is we've cooked up this set so that h zeta is discrete harmonic on the whole set. And all its boundary values are this 1 over 2 zeta, except the boundary value at zeta itself is constant order between 1 and 2. And the value at the origin will also be important. That's 1 over zeta. Okay. And then because this green function, or this potential kernel, has those good asymptotics, you can show that this set omega zeta is really close to a ball. So it only differs by a constant amount in the radius. It contains a ball of radius norm of zeta minus a constant contained in a ball of radius norm of zeta plus a constant. Okay. And the other thing very closely related to this first lemma that you need to know about this set omega zeta is that is a mean value property. So if you take your harmonic function and you sum it over the lattice points in omega zeta, well, so you sum h zeta of z minus h zeta of 0. If h zeta were in the continuum, if this sum were an integral, then you would get just 0 by the mean value property of harmonic functions. You can't expect to get exactly 0 in the discrete case, but you get something very small, so only like log of zeta. Okay, so we're almost done with the kind of setup, and we can actually get to the proof. So the last piece of setup is that we've got this discrete time martingale, but we really want to have a continuous time martingale. So what we can do is, instead of running discrete random walks, we can run Brownian motion on this grid. So and we can define our martingale was defined in discrete time by just summing the discrete harmonic function over the cluster. Now, to make it a continuous time martingale, we just add one more term, which is also the value of the discrete harmonic function at the currently active, wherever the currently active walker is. We add the value of the function there. Okay. So then we have a continuous time martingale, and the reason we want that is to be able to use the martingale representation theorem, which says, well, we can represent this martingale m zeta as a random time change of a standard Brownian motion. So this time change is the quadratic variation of the martingale. So the limit here is over all refinements of the interval from 0 to n. Okay, so now we can see how the proof actually works. So we want to prove this lemma, which said that if there are no L late points, and M is like a large constant times L, then with high probability there are no M early points. So what we're going to do is break up the thing we want to show is unlikely into a union of a bunch of events QZK. So QZK is the event that Z joins the cluster at time k. Z is M early. This here is just a reminder of the definition of M early. No previous point is M early. And finally, no point is L late. Okay, and now, given Z and K, we're going to pick a martingale to use to show QZK is unlikely. And so that means we have to pick a zeta. Where's the pole going to be located? And it'll be located close to Z, but slightly further from the origin. So the picture is that we have this early point Z, and we have our martingale m zeta, and we're going to place the pole. Here's the origin. We're going to place the pole just slightly along the ray from 0 to Z, but slightly further along.
So zeta does not have to be that.
I don't know. Probably it should be a lattice point. So let's take the closest lattice point to this. Okay. So how are we going to show this event is unlikely? Well, okay. Maybe read the bottom line first. So the goal here, where we're trying to get, is a large deviation for this Brownian motion. And the Brownian motion came from the time change in the Martingale representation theorem. So basically, we're going to somehow show that this event would imply that this Brownian motion, if you run it for a certain time s, exceeds s, somewhere in the time interval from 0 to s. And that's an event that's exponentially unlikely in s. And the time s that we're going to take is logarithmic in n. So in the end, we'll get something that's polynomially unlikely in n. OK, so how do we get there? Well, observe it would be enough to show two things. So on this event, we'll show that with high probability, this martingale is pretty large. And also with high probability, not that much time has elapsed. Okay, so do people agree all we need to do is show 1 and 2? So just to say it one more time, so on this bad event, we're going to show the martingale is likely to be large and the elapsed time is likely to be small. And when you put those together, you get that this Brownian motion had to become very large in a very small amount of time.
No late point is used for the fact that the martingale has to be large.
Yes. Yeah, so James raised a good question. Where do we use the no late point? So I'll be sure to point that out. It's coming up. So, okay. So why does the martingale have to be large? Well, remember we have this a priori estimate that said thin tentacles are unlikely. Okay. So we know with high probability this. So we've got this point Z, which is our early point, and not only does Z belong to the cluster, but a large number of particles nearby belong to the cluster. Specifically, a constant fraction of the area of this ball. So this distance here is order m. So a constant fraction of the area of this ball, Bzm, has to be filled up already by the cluster. So here we have order m squared points in this ball, Bzm, that also belong to the cluster An. Or maybe it's AK. And okay, and how much does each contribute to the martingale? So remember, our H zeta was like real part 1 over Z minus zeta. So it decays like 1 over Z, like 1 over the distance. Okay, so each of these points contributes. Sorry?
How do you know the sign?
So all the sign is always positive. So the negative, it's in this half plane our function is positive, in this half plane it's negative.
How do you know that all these points are in?
Okay, because of our stopping rule. So remember we are stopping our points when they exit this level set omega zeta. That's the level set of a positive number. So everything, right? It's a harmonic function. It's positive everywhere on the boundary, so it's positive on the inside. So this.
When you say you stop it, so what does that mean?
Okay, so it means when we run our ideal A process, we will stop a random walk either when it reaches an unoccupied site or when it reaches the boundary of this set omega zeta.
In the second case, what do you do with it?
It just stays there.
So it could be in between two lattice points.
It could be in between two lattice points, and there could be many particles accumulated there.
Right. And so your theorem about thin tentacles are unlikely, your lemma applies in this case also. That's what you're using.
Which lemma applies in this case?
Tentacles are unlikely.
So I think we are using it for the actual set AK, but it's also true of this modified set. So yeah, that's a good question. So I would have to look at the proof again to know which set we're using it for. But yeah, I mean, let me come back to that if there's time. I think it's true of both sets. Okay, yeah. So Russ's original question is, how do we know this contribution is positive? So the point is, this function h zeta is constant equal to 1 over 2 norm of zeta everywhere on the boundary except at zeta, where it's order 1, and it's discrete harmonic. So certainly everywhere on the inside it's non-negative. Okay. Right, so we're trying to argue that the martingale is large on this event, and the point is that because of no thin tentacles, we know that a lot of nearby sites are occupied, order m of them, and each contributes order 1 over m to the martingale, because this function decays like 1 over the distance. So, okay, so we get a total contribution m squared times 1 over m, so of order m. Okay, so the one thing we need to be careful about is why do we know that contribution isn't swamped by the rest of the picture? Because, you know, this tentacle is tiny, right? M could be as small as log n. So, you know, we've got a huge number of other sites out here that are also all contributing to the martingale. Why don't they just bury this contribution? And that's where James's question comes in. So this is where we're going to use the no late points. And so the thing to observe is that, well, what does no late points mean? It means if I go just a little distance inside, I know that all the sites in a slightly smaller ball were already occupied. So this smaller ball, B r minus L, is completely occupied. Okay, now what's the contribution of sites in this ball to the martingale? Well, it's very small by the mean value property. So this entire ball, B r minus L, contributes only constant log r, because its total contribution is the sum of a discrete harmonic function over the ball. Okay, so finally, well, okay, that takes care of most of the points, but there's still a fair amount left. So why can't they destroy this contribution of order m? Well, what's the worst that could happen? So, yeah.
This harmonic function is h,
H zeta.
which is not negative.
Yeah. So the martingale is defined by summing. So m zeta of n is the sum over the cluster of h zeta z minus h zeta 0. So, and remember that h zeta 0 is 1 over norm of zeta, and h zeta everywhere else on the boundary so everywhere else on the boundary it's 1 over 2 zeta, except at zeta. Okay, so that means from a single point, you know, the biggest negative contribution we can get from this sum is minus 1 over zeta. Okay? So we only have, if we started with pi r squared points. Can people see down here? No. Okay. So
Remind me, how big is norm zeta? R.
like r.
And how does that relate to m?
M is tiny. M is like potentially as small as log. Okay, so we started with pi r squared particles, and most of them got swallowed up by this ball. Okay, so how many are left? Well, about r times L. Okay, and so this is leftover particles that could have a negative contribution, but each contributes the worst it could be is if it contributed minus 1 over zeta. Okay, so total you'll get at most yeah, so this is basically minus 1 over r. So total you get at most minus constant times L. Okay. And remember our arithmetic here was that m is larger than large constant times L. Okay, so this is not enough. Oh. Okay, this is smaller than in absolute value than this. Okay. All right, so that was one of the things we need to do. But we also need to know that so we know the martingale is large. We also need to know that the elapsed time was pretty small. Okay.
So far, we didn't really use that it's found in motion.
Well, we used this. We used this fact.
This is true for martingale.
Mhm.
Martingale is bounded.
Right. Mm-hmm. Yeah, so if you're asking why did we have to go to continuous time, we didn't really have to. It was convenient, but you could do it without that device. Okay, so we want to show the elapsed time is small. And so here, what we're going to do is take this quadratic variation time change and look at its increments. And what we'll show is that they're independent standard Brownian motions such that these increments are bounded above by the exit time of these Brownian motions from a certain interval.
Why are the martingales bounded jump? That's what.
Stochastically bounded. It's not bounded.
Yeah, so
Exponential boundaries.
So what's going on here is pretty simple. So we're going to see, well, what happens if we look at, so inside this time interval from I to I plus 1, that's when we just have a single particle walking around. It hasn't yet found an occupied site. So if we take, m, so I is an integer time and t is in interval 0, 1, and we look at the martingale at time I plus t minus at time I, that's just the value of this h zeta at the current location of this. So I write beta t for the Brownian motion on the grid. Okay, and then I use the maximum principle for discrete harmonic functions. So I don't know where this Brownian motion currently is, but I know it's somewhere inside the set omega zeta. So this h zeta bt is at most, well, this is really bit, it's the ith Brownian motion. So it's at most this bi and at least this ai, where these are just the min and max over the current cluster. So this is by maximum principle.
So when you said that with the boundary, did you not mean to put boundary?
No, I did mean to put boundary because
Aren't all the boundary values the same except for one zeta?
except for zeta, yeah.
So you know what these values are.
Well, okay, that's for omega zeta. They're the same, but this is the boundary of this random set AI. So we haven't.
Oh, right.
Yeah, so the boundary values are all
Right.
different
Right.
for AI. Okay, but the point is, because h zeta is harmonic on AI, because AI tilde is always contained in omega zeta, then the maximum and minimum over A tilde are the same as over the boundary by the maximum principle. Okay. Okay, so this means that if you combine this with the m of t is b of s of t. So our martingale is this random time change of Brownian motion. So it's saying that so if I take b of s of t plus I minus b of s of I, that's bounded between ai and bi. So that says if I take, so I want to come up with these independent Brownian motions, I should take this bi to be, bi of u is b of s of I plus u minus b of s of I. And that will be bounded between ai and bi, and these are independent for a different I by the strong Markov property. So yeah, so that's all that's going on. It's basically the maximum principle. Okay, and right,
Sorry, at this point you could ask why you're using, now it seems to get more difficult because you're using a Brownian motion. So at this point you can ask what's the benefit of using a Brownian motion?
I guess the benefit is it's easy to control the large deviation of the first exit time of a Brownian motion from an interval. So, right, I mean, we want...
no, but you're just controlling the increments of the martingale to,
Right, so, okay, so to prove this bound, you had to work slightly harder because of the Brownian motion, but now the payoff is now we just have to do large deviation for this simple one-dimensional thing about Brownian motion exiting from an interval, and that's something relatively straightforward. So, so in particular, you could show that expectation of e to this exit time is at most 1 plus 10ab, where a and b are the minus a and b are the endpoints, and okay, so then writing the time change as the sum of its increments, that's bounded by this product of expectations of e to the Brownian exit times. And okay, and then it's relatively easy to estimate these ai and bi's. And what you get out of this is that on this event q, so this expectation of e to the quadratic variation times the indicator of q is at most, grows at most polynomial in n. Okay, and then by its Markov's inequality, you get this. Okay, so I showed you the proof of one of the two lemmas. The other one superficially looks very similar. It's all the same ingredients. Maybe I cheated because I showed you the lemma that doesn't give you that extra savings that makes the whole thing work. So I can try to go through that, but in case I run out of time with that, let me just say what changes in higher dimensions. Well, you have to choose this function h zeta looked like it was using some complex analysis with this 1 over z, but really what we're using is something like the Poisson kernel. So it's like a discrete Poisson kernel. So essentially the harmonic function we're using is 1 at the point zeta, 0 at all the other boundary points, and take the harmonic extension of that. So that's what you can use in higher dimensions. And when you go to estimate the quadratic variation, you find that it's actually constant order in higher dimensions instead of logarithmic. And what this means about the fluctuations is they're dominated by a different effect. So rather than having kind of large portions of the boundary that are a little bit further out or further in than you would expect, it's really these tiny features that are dominating the fluctuations, the thin tentacles, which, as we saw, at least heuristically, can grow to this length square root of n by this very simple mechanism of traveling straight up every time. And so that's formalized in this paper of Asselah and Gaudier to show that actually you do get fluctuations of order square root log n in all dimensions. And this leaves a gap only in dimension 2, where we believe that the fluctuations are log n, not square root of log n, but the lower bound is still open. Okay, I'll stop there, and if you really want to see lemma 2, I can do that. Thanks.
Questions?
Yeah.
What is the strategy that the other people use?
Okay. I mean, I can't say I read their paper line for line, but roughly what they seem to do is define a different process whose fluctuations are easier to handle, and then construct some complicated coupling between that process and IDLA. So the difficulty of that paper is in verifying this coupling, and that portion of it I have no real insight into, so I won't say anything further about it.
For the equal one, it says square root of n.
Yeah, d equals 1, right. So this is a fun exercise, that fluctuations there are square root of n.
So, well, ask the other question. Right? So, is the log n, can you relate it to maximum of the Gaussian free field?
Right. So, okay. Right. So another way that you could try to analyze the fluctuations, instead of being very picky and asking for the absolute furthest lattice point that's occupied or the absolute nearest that's unoccupied, you could sort of take local averages, and then we can show that the fluctuations scale to a variant of the Gaussian free field. So, okay, so the question is, is this log that we're getting related to the maximum of Gaussian free field? I mean, I think morally the answer is yes, but
how big do you have to average in order to see this Gaussian field?
I mean,
when you say the fluctuations converge to GFF, in what scale?
So we prove it on the constant order scale. So you really are averaging over a constant fraction of the picture. Okay. But maybe it's true on smaller scales, and that's maybe that's what you would need to look at to answer Yuval's question. So I guess I'll mention, related to that is another question which I think is still open, although that most recent paper of Asselah and Gaudier does say something about it, which is fluctuations in a fixed direction. So what we've bounded here are fluctuations in the worst case direction. Suppose you just look along the x-axis and you want to know, what's the furthest side along the x-axis that's occupied. So we believe the answer there is square root of log in 2 dimensions. And I think Asselah Gaudier have one side of that, but not the other. So.
And constant in higher dimensions?
Yes, constant in higher dimensions.
So that's completely consistent with the picture for the Gaussian.
Right.
So I just want to make sure I understand what you were just saying about averaging Gaussian free field. In this picture, you have positive and negative color, but instead if you color by the number and then average instead, you would have a scaling which is Gaussian free field. That's what you're saying?
Yes. So the thing that scales to Gaussian free field is you take this picture, but you shade it red or blue according to how late or how early the point arrived to the cluster.